Code Review, the series where you guys send me your amazing projects and I roast and I take a look at them. Quick reminder, if you have a cool project that you want me to take a look at and give some feedback on, chernoreview@gmail.com is where you can send in all of your stuff. There are some details in the description of this video. Today we're taking a look at grass rendering in OpenGL/C++ for Code Review series by Some Pineapple. Hey Jan, my name is Nathan, I'm 15 years old and I've made a scene in OpenGL with a lot of grass. I was inspired to make this project after seeing a YouTube video from Ace Roller titled Modern Foliage Rendering. I have seen that video, I believe, so I think I know what he's talking about, though many of the techniques I use are different than what he did. Feedback I'm looking for. Optimizations. I think, oh, here's a nice little screenshot. That's cool. Okay. That does look like a lot of grass. Optimizations, I think is running pretty fast already, but I'm sure there is room for improvement. And also code structure/memory management. I learned C++ mostly off of YouTube, and it was after writing Java for a couple of years. It wasn't until about 6 months ago I learned that all my previous code had been full of memory leaks because I used a new keyword everywhere without cleaning things up. Okay, cool. So we've got a 15-year-old who has mostly learned C++ off YouTube, and there may be some optimizations, but also code structure/memory management is what they want us to take a look at. Thanks so much for reading my email. Best, Nathan. I develop on Linux, but all the dependencies included is Git submodule, so it should compile fine on Windows as long as you clone with the recursive flag. Cool, let's get this running. It's running. I don't know why I keep clapping. So here we have OpenGL grass. FPS is not bad. There's quite a lot of grass here. I have no idea how many blades of grass we're rendering here. It looks like I can move around with WASD keys. I can't seem to move around with the mouse at all. Like, there's no rotation, which is a little bit underwhelming. I would have loved to have seen some rotation because I can't even really inspect the grass, and I can't get lower either. It's just WASD, I think. Also, this window is like, what is this, like a 1-to-1 aspect ratio, and also not resizable. Like, what is going on here? But hey, like, it works. It's pretty cool. I can just, is this like going to be like an infinite kind of environment? I can just keep going forward and maybe the chunks will like replace themselves with where they are. Definitely pretty cool though. You can see that there's like some subtle movement as well. Each of these blades of grass are kind of moving. I would like to have seen a little bit more variation with the color, and also it does look like there is some darkening as it gets lower, but perhaps just not quite enough darkening to kind of simulate that ambient occlusion. I could talk a lot about grass rendering, by the way, but I'm going to try and restrain myself here. Yeah, I think we might jump in and play with some of the colors at some point today, just to try and make this look a little bit more realistic, perhaps. I've spent some time outside today. Looked at some grass, so I have a pretty good idea of what it looks like. And this is not bad, but I think we could improve it. All right, let's dive into the code. Oh look, define window width, window height in the main.cpp file. So let's just, what happens if we make this like a little bit bigger? Is this gonna fall apart? Yes, it is. Okay, so now you can actually kind of see the edges. Ooh, and if I move, you can see the edges of these chunks. Right? So it's offloading the chunks that get out of like the camera's frustum. But unfortunately what's happened is I think that that kind of square that we saw in the beginning, that was basically like the camera's frustum. It still thinks the camera size or whatever, like the view that the camera can see is still confined into this area, which is why, for example, like this chunk gets unloaded. This one might remain just because it might look like this or something. There might be part of it intersecting that camera frustum. But it's cool to kind of see, I guess, this like frustum culling, you know, chunk culling, you know, system, I guess, working when we make the field of view of the camera wider by just making the aspect ratio wider, because that's basically what we did. The FPS note hasn't actually fallen. It's like exactly the same as what it was when we were looking at it at 1000 by 1000, which we've basically doubled the amount of pixels. We went from something that was 1000 by 1000 to now 1920 by 1080, which is about 2 million pixels versus 1 million. So we've doubled the number of pixels. The resolution is twice as high. However, the FPS stays the same. And that, of course, is because there's not much fragment like shading going on here. The pixel shader is probably quite light. It's really just the number of like triangles that we're rendering here that we're pushing through is probably very high. I'm interested to dive into the code and take a look at how this is drawn. I'm pretty sure these are just going to be, these do look like individual pieces of geometry that have just been instanced like a bajillion times, which is pretty like standard, fairly decently performant way to go. And then I'm going to take a guess that this kind of swaying that's happening here, that also seems to be based on the height of the vertex that makes up a grass blade. So if we have this kind of grass blade over here that looks like that, the higher we go, the more we move it. And then the lower we are, the less we move it, because the base shouldn't move, obviously. We don't want our grass going like this, but we do want it kind of swaying like that. And that's probably just animated using... Actually, it does look like each individual grass blade does look to be on a different path. Like maybe the movement's the same, but it's on a different stage of its animation, which makes me think there's probably some kind of position-based attribute there as well that maybe will tie into like some kind of sine wave or like some kind of like sine or cosine function basically that will just oscillate it back and forth, but at different kind of stages of that graph. And that kind of makes them all look independent, which I don't know, like I have mixed feelings about that, because obviously like whilst grass maybe does move slightly differently, like each individual blade of grass will move maybe a little bit differently compared to like the ones next to it. Overall, the wind blowing on it is going to be like the same, right? So like this chunk of grass blades is going to have the same wind force coming on it. There might be other factors, like certain blades might block the wind from other blades, I guess, but overall they should more or less have the same effect, or at least be in larger chunks. So there are some things, as I said, I could talk about grass for a very long time. But yeah, those are kind of my thoughts. In general though, pretty cool system. I like the fog as well. The fog looks pretty nice. There's that kind of fade out that we see here. I don't know if that's going to be based on the actual distance of the grass from the camera, or just like as in if that's calculated using like say a depth buffer, or if that's actually just like the literal position compared to the camera. Because if grass is the only thing you're rendering, which of course is the case here, then you can just kind of hack it. You don't really need to, make it work with other 3D objects or anything like that. Now, if you're new to programming and you want to develop your computer science skills a little bit further, as well as learn some math, then I highly recommend you check out Brilliant, the sponsor of today's video. Brilliant is an amazing website filled with lots of courses on various STEM topics. It is by far the best place to learn all of this because of how interactive and engaging it is. Hands-on experience is the best way to learn anything, and Brilliant gives you that experience by not just teaching you and throwing information at you, but also getting you to engage with the content, quizzing you about what they're teaching you, and showing you how things work visually. Now, I'm a fairly experienced programmer. I've been around the block a few times. However, math is something that I constantly want to revise. I've been going through Brilliant's calculus courses to revise and make sure I know everything I need to for the ray tracing series, which, by the way, did I mention that because their lessons are nicely organized, you can just spend like 15-30 minutes a day going through all this stuff. You don't have to commit hours. If you only have a spare moment, you could just do a lesson or two. And that kind of consistency is really important. If you can just spend a little bit of time learning each and every day, you'll get very far. And if calculus is a little bit too advanced for you, want to kind of start at the beginning, then Brilliant have this brand new everyday math course that will put you on the right journey. The best thing is that you can get started with Brilliant for free. Just go to brilliant.org/thecherno. Link will be in the description. However, the first 200 people who sign up using my link in the description below will get 20% off an annual membership. So definitely hurry and do that. It's a great way to commit to being consistent in your learning. Huge thank you to Brilliant for sponsoring this video. All right, so since code structure was one of the things we should be reviewing, let's just take a quick look at this. So we have a main function and we have like most of our application over here. I would definitely abstract this a little bit. The reason being that this will just continue growing. In kind of a more real application, the complexity of this section of the code is just going to explode. For something as simple as just a little grass test though, it's hard to kind of give advice sometimes, because if this is the entirety of the application, can I really say that, oh yeah, it's going to grow, it's going to explode, it's going to get so much bigger? It's like 90 lines of code. This might be the whole program. So why complicate things and over abstract things? That's a good point. It really does make it difficult to kind of code review certain applications, because I'm not sure if this person wants me to kind of assume that this is like just how they would write a program and guide them into the right direction for writing larger applications, which they might potentially do in the future. Or if I should look at this product as a whole. Let me know what you guys think in the comments below, because honestly, like this is one of the things that gets me every time. Ignoring that though, we initialize GLFW, we set some OpenGL context stuff, we create the window over here. I don't really like this asterisk for the GLFW window pointer being like in the middle. I think that's a bit weird. I know some people do that, but I think that's a bit weird. I personally like writing it next to the type. However, some people like writing it next to the variable. That's fine. You do you, but don't leave it in the middle. Who's middle gang? Like if you guys are middle gang, let me know, but that's just weird. All right, GLFW swap interval 0, which is going to disable vsync. We create the OpenGL context here and tie it to this thread and that window. And then we're using glue, but like GL3W to just get some OpenGL extensions going. And then we have our shader, our mesh, our grass renderer, and our camera. Fairly neat. I like the fact, obviously, that these are not heap allocated. Like you mentioned, they might have been. It's very common for people coming from Java or C# to just make objects like this in C++ because they consider that to be the equivalent, which in a lot of ways it is, because pretty much everything is heap allocated in Java, and in C#, like you have structs which are not heap allocated. However, classes obviously are, and since shader is a class, this really is like the equivalent. However, C# and Java, they have garbage collectors, which means, of course, that your memory will just be cleaned up automatically after it hasn't been used for a while. In C++, that of course is not the case. If we create this like this using the new keyword and it's created on the heap, we'll have to delete it somewhere. But that's not the only consideration. There's also a performance consideration, because if we're making things on the heap, we have to find a free chunk of memory, which will slow down the allocation process, but then also that memory is likely going to be somewhere else inside our RAM. And if we're dealing with like fragmented memory, that can slow down our program every time we need to read and write to or from that memory. So those are basically the reasons for why you don't want to like heap allocate this using the new and delete keyword, but instead you just want to use the stack as much as possible. The stack will always be hot inside our memory, inside our CPU cache, because, well, we're reading from the stack constantly and writing to it constantly as we progress through this actual function. So of course that's going to be okay. All right, so yeah, we load this shader. I'm assuming we just basically load it using OpenGL. Yep, we just load the actual shader text and compile it, which looks pretty good. We're even deleting it at the end here, which is good because we want to delete the individual like shader intermediates basically, and we link this all into our program, which of course we don't delete until we get to the destructor, which yeah, it doesn't exist here, so we're actually not freeing that program. What you should do is create a destructor here for your shader class, and then have that actually called gldelete program so that you can actually get rid of your shader program. Speaking of which, one thing I would do, which you don't have to do, I know some people don't like to, and that's okay, is use some kind of convention for your naming, like for variables, right? So what I would do is, instead of just having this written as shader program ID, I would rename it to m_shader ID. M here stands for member, because it's kind of like a member variable that's private. I do this for my private, like non-static member variables. The reason why I do that is because it can be a little bit confusing when you look through this code to just see this and be like, okay, is this something that belongs to the class? Like, is it a member variable or is it a local variable? Of course, there are things like syntax highlighting. In fact, you can see that these are a slightly different color from this. And the reason that's happening is because I have a slightly different color for my local variables than my like member variables. However, that's just something I'm used to. And again, I did say that it's okay to disagree and you can do whatever you want, but I like doing that because in my experience, I've just found in larger projects, especially when it happens to matter more, if stuff is like a member variable or a local variable, this can really help kind of readability at a glance, just to see like, okay, what's going on here? Okay, I can kind of piece this together. The other thing you should do is, well, the other thing I would do is initialize my variables. So shader program ID here is not assigned to anything, and you're also not assigning it here. So there are two ways to initialize this variable. You can either just write =0 over here inside the header file, which is what I would do, or you can alternatively use this little colon over here, which looks a bit weird, and then just set a value like this, right? I mean, you could also set a value like that. That's totally fine, but this will kind of initialize it before it gets into this code. Why would you do something like this if you set it over here anyway? Well, first of all, functions like this can fail, right? Like, for example, you may not have loaded that function, and so it might fail, right? Or something could happen here, like you could get a crash somewhere here. And if you get a crash somewhere here and you're debugging and you take a look at this shader program ID and it's some random value, that can really throw you off. Or alternatively, if something like an exception happened inside one of these functions, it didn't execute the rest of this function or whatever, you have a shader with a shader program ID of 0. So you can tell that this has not been created, right? You could also kind of set it back to 0 like a pointer once you've deleted it here. However, I wouldn't really do this in the destructor because that object's going to die anyway. But my point here is just that, like, in my experience, I found that it's really, really, really useful to have variables properly initialized, because when you are debugging something, it just helps tremendously to be able to see what state your kind of objects and variables are in. And if it's just random uninitialized memory, then, well, yeah, good luck. It makes stuff a lot harder. There's that middle pointer gang again. So we get uniform location by const char pointer, which is okay. OpenGL functions take in a const char pointer. Personally, I wouldn't. I would take in either a string view, or there's my little string view, or I would take in like a const std string. However, again, the OpenGL API does take in const char pointers, so I'm not going to fault you too much for that. Look at my failing of typing out string view there. You should probably also pass large objects by reference instead of by value. So a mat4 is 64 bytes because it's got 16 floats inside it. So I would change this to be a const reference because that will avoid copying that memory. Fun fact, we were working on something back in the day at EA on the mobile engine, and we found that we had like a function that passed in a bunch of these mat4s, basically, not like GLM mat4s, but our own math types, but there were 64 bytes, and we found that the program would perform faster if for one of them, I think it was the last parameter, if we made that be by value and this to be by reference on like some Android ARM device probably. So anyway, moral of the story is my general advice is, yes, that's 64 bytes of data. Let's not copy it. Let's just const reference it. However, yeah, from my story, you can see that sometimes that's not that's not necessarily correct. Let me just restore this as well. And then we'll be back to normal. And especially because, like, there's no reason for this to contain a copy, of course, of this data, because at the end of the day, all we're doing is obtaining like a pointer to that memory buffer and passing it to OpenGL anyway. Speaking of which, you have a false here. However, this takes in a GL boolean. This is something that probably isn't a big deal in practice, but because a GL boolean, if we take a look at a GL boolean, you'll see that it's actually an unsigned char. Right, so it's like a 1 byte kind of integer type. It's not an actual boolean. I mean, booleans might not really exist anyway, but they do in C++ technically. So because of that, what I would do is I would use GL false here instead of false. Again, realistically, you're probably not going to see any difference. False is usually going to map to 0. However, that does make me feel a little bit uneasy, so I would just use the correct kind of term here. And GL false, as you can see, is just defined to just be 0, which of course is the right type for an unsigned char, which is what that GL boolean is. That's the kind of main point here. The underlying type is an unsigned char. Therefore, I would feel better providing it with an actual unsigned char. Getting back over here into the main class, we have a mesh class. So mesh and floor mesh. I said main class. This is just a main function though, so forgive me. Mesh, floor mesh, and then we load this assets plane.obj. Probably could just generate like a plane instead of having to load it in from like an obj, but that's okay. You got an explicit mesh constructor here, okay, and then that takes in a const char path. So again, you're taking in a const char path. Now, realistically, this is a const char, right? So sometimes when I'm kind of talking about C++, it's very common to kind of want to use strings potentially. And so people end up like overusing, I guess, strings. But then there's also the flip argument where if you actually define like a string literal like this and you look at it, it's just a const char array, because this actual string is going to be like compiled into like a read-only memory section of your binary that is going to be this resulting program. It's physically going to be there inside like the binary data, and this is a pointer to that like read-only block of memory. If this did take in like an std string, then it's a little bit annoying in a way, because what would happen is this const char pointer would have to be used to construct an actual string instance. So string will have a constructor that takes in a const char pointer, and now we're actually making an object implicitly by just passing in like an actual string that we've hard-coded into our C++ code. And that can be bad. Like, strings can dynamically allocate memory. That could result in a heap allocation. There is something called small string optimization. If your string is small enough, it will just store it on the stack within this string object, which will be faster. But even faster than that, it will just be to use a const char pointer. And that's why, like, in a lot of cases, I do like using string view, because string view at its core, it's just a pointer to like just a a character array, and then also like a size associated with that array. And so in other words, it doesn't store anything. It can point to either an actual string and its allocated memory in a kind of a non-owning way, so it's not going to like copy it or delete it or anything like that, or it can point to a const char pointer, and that can be used for your kind of compile time strings. So I would really recommend that you take a look at string view, because it's just it's a great little utility class. In the past, in larger projects that I've worked on, we had like back at EA, we had like our own like string class. I think it was called like symbol or something like that. And basically what symbol would be is that would represent something that would actually be like a compile time constant string, versus like, you know, I think we had like our own string class, which would represent like a dynamically allocated string. So strings, like string semantics and everything, like there's a lot to talk about there, almost as much as I could talk about grass for. All right, speaking of which, I didn't actually take a look at the mesh class, but we read in that OBJ, and because it's an OBJ, OBJs, for those of you who don't know, very, very simple format. Let me see if I can bring one up. So here we have our plain OBJ. You can see over here that it's been created with Blender 3.1.2. We have a little material library. There's an external file that's pointing to here. We have an object called plain, and then this is all of the vertex data for it, but it's not actually all of the vertex data. It's specifically the vertex positions. So they're marked with V, even though they're not the whole vertex, they're just a position, and they're listed over here. And then if we scroll, this is a very, very like tessellated plane. Look how many vertices, 56,000 vertices for a plane. Okay, that's interesting. I don't know why it's so dense. Maybe he's using the vertices for something, right? So if you're using the vertices for something, maybe you want them there to be like a lot of them and placed kind of at certain areas. I'm not sure. Maybe they're even being used to spawn the grass, although I don't think so, because they look pretty like evenly distributed. All right, then we have VT, which is like the UV coordinate of each vertex. This is like, yeah, this is 263,000 lines. And then we have these faces, which are basically indices that make up a triangle. So this index, like the vertex at this index, the vertex at this index, and the vertex at this index creates one triangle. And then we have 3 of these. Actually, no, sorry, I'm wrong. This is the vertex position, this is the texture coordinate, and then this is probably like the normal or something. So this is like the vertex position, the texture coordinate, and the normal. And this is one vertex, one vertex, one vertex. 3 of them make a triangle, thus making a face. And that is our little OBJ format. So we read them in using utils load OBJ, which will basically parse all of this text. Another reason why like OBJ is not a great file format. I mean, there's lots of reasons why, but one of them is it's all just like text. And so it requires a lot of string parsing, which is not the fastest thing to do. So this will take a little bit of time. Yeah, so here V is vertex, which again, I would not call it a vertex. I'd call it a position or a vertex position, because this whole thing is a vertex. And then we have a normal, potentially if we have that. There's actually one more OBJ. There was this other OBJ called grass.obj, which looks like this if I take a look at it in Visual Studio's model viewer, which is quite fun to look at. You can kind of see, I don't know how to zoom in here. Oh, okay, I can zoom in, but the near plane is a bit okay, there we go. The near clipping plane, this must be quite small, because if I zoom in any further, it clips it. But you can see kind of the triangles that the grass blade is actually made out of. And then if we take a look at it, at the actual file, this one's not very big, but it's got our vertex positions, our texture coordinates, just a single vertex normal at -1 on the X. And then we have our faces, which is basically going to be used for our index buffer. So yeah, that's cool. We triangulate it. This probably isn't, I don't know if triangulation is going to be necessary, because so far all of the meshes we've looked at are already triangulated. Like if we look at these, you can see they're all, like we only have 3 components to a face. It's not like they're quads, because if they were quads, we'd see one more here, because we need 4 vertices to make up a quad. But I guess maybe this is just something safe to do. But either way, this will basically build up our vertex, which contains a position and a normal, and that will be used to create a GPU side buffer and upload the data to the GPU. And then we define the attributes. All pretty standard, nothing too special going on here. We have a render instance function, which is a little bit fancy. So yeah, we are probably using instances. And so that will draw triangles. If we just take a look at this function quickly. So we have first 0, and then count is vertices.size. Vertices.size. Oh, right, that's because draw arrays. So the draw arrays part, this is how many vertices we're drawing. We're not using an index buffer at all here. And then instance count is how many instances of this we want to draw. Okay, cool. Going back to main, grass renderer. Yeah, like, to be honest, so far with the code, like, there's little things I'm noticing, like, for sure. Like, for example, unsigned int, like, you shouldn't use that. Use uint32t instead. However, like, you know, and then obviously none of these are, like, initialized. They should be. You're probably initializing stuff like start time, I imagine, otherwise. Oh yeah, and you know of this way of initializing it as well. Your code style in general, I would not use this. I would, you know, drop this down here. I would make sure that my curly brackets here are on new lines like this, because that's kind of the convention. Don't worry, I know you're coming from Java. When I also came from Java into C++, and for a while I used to write code like this as well, and I would like literally almost fight people for wanting to drop this onto a new line. But then I started working at EA and kind of humbled myself a bit and more or less adopted their code style and the more kind of common C++ one, which is dropping it onto new lines. So I get where you're coming from, but I would personally make that change. It will make the code appear a lot cleaner and easier to read because it's just going to be less dense, basically. Okay, so the grass renderer is probably the biggest kind of thing to look at here. I know I've probably spent a little bit too much time on the other things, but I just wanted to kind of be as detailed as I can. Okay, so basically, if we look at this, yeah, sure. So we create, we get these kind of like projection matrix, view matrix and time, uniform buffer objects, they're called here, but I don't think they're. Let's actually take a look at the shaders, because this will help understand this. Where are the shaders? Okay, I want to look at, so this one's called grass vertex.glsl, and then we have grass fragment.glsl. So if we look at the vertex one for a second, yeah, like projection matrix, view matrix, and time, they're not uniform buffers. They're just uniforms. So I don't know if UBO is a good name for them. SSBO, so that's like some shader storage buffer object, I think it's called. That's going to be this buffer here. In other APIs, we just call them like buffers or like storage buffers. So I'm not really that familiar with like the OpenGL kind of term for this, but this is just basically a storage buffer of all of our grass positions. And then we set start time to current time milliseconds. That's interesting, which will get the current time, I guess, time since epoch in milliseconds. I also wouldn't probably write it this way. I would just set my start time to like 0 so that I get a predictable start time every time. And then every frame, I would take in like a time step and increment it by the time step, essentially, right? So that will always get basically the current time in milliseconds or in seconds or however much I want it, but it'll kind of, I guess, start at 0 and just accumulate instead of having to do all of this like stuff every time you want to calculate the current time. You just increment it by the time step and pass it in and you're done. Now we do create the storage buffer here. So we have a shader storage buffer. How big is this guy? Bind buffer base. Oh, I forget about this stupid, like there's like some bind buffer and bind buffer base. Like, I don't know, I feel like OpenGL is sometimes even a bit complicated. Like, I guess this is, I think this code from memory binds it to this binding equals 0 thing. I think that's why the 0 is here to bind this actual, this is just creating like a buffer, I guess. And that's binding it to this spot in the shader, which yeah, is a bit weird. The way that works. Okay, cool. Still not seeing that buffer get populated anywhere here, but we are, looks like we are actually binding it. But we also have this grass chunks here. So grass chunks. Okay, so grass chunks in place back, and then we have a grass chunk size here of 0.5, and we create this kind of grass chunk class instance here, which has a grass start, grass stop. And it creates a bounding box for it. Yeah, like I wouldn't initialize a random device and random engine for each grass chunk. This is probably something you could definitely optimize, because you're probably creating quite a lot of these grass chunks, right? Like if we look at the console, it said you created 40,000 of these. So you're doing this 40,000 times, whereas like, I mean, you know, this distribution, sure, you can leave that in because the scarcity kind of defines it, but this stuff, man, like I would bring it out here and just make it static like that, because there's no way that needs to be initialized every single time. And then over here in render, okay, right, so over here in render you're calling GL buffer data with that. Oh, okay, this I don't think is the best idea. So you're going to eventually draw the instances here. Okay, I see. So you're not using, you don't have like a transform buffer or anything. Instead, what you've got is this storage buffer of grass positions, which, well, there's a lot of stuff going on. There's a lot of stuff going on here in your vertex shader. Wow, okay, probably too much. Yeah, there's like some wind, variance, rotation. Yeah, there's quite a lot of stuff. I probably wouldn't do this much work here in the shader. I would probably maybe expand your grass positions buffer to have a little bit more. So for example, like you have a rotation that you apply here, it looks like. So okay, so let's kind of look at this shader. So first of all, we have like our grass position, which we retrieve from this storage buffer. So we have a bunch of vec2 grass positions. Why are they vec2s? Because if you look at like a plane with all of this grass distributed, obviously we don't care about the height of the grass. It's all at the moment going to be on this plane. And since it's on this flat plane, then we only need an X and a Z position. We don't need a Y position. Hence the vec2 is what I'm assuming. Now, this obviously is not going to work if instead of a flat plane, you actually have like some kind of terrain going on. In that case, you probably need to maybe look at like the closest vertex or something, or like a point within a triangle, I guess, to see the X, Y, and Z so that you can actually kind of have grass growing from a, let me switch to green for grass. You can have grass growing from like a specific height level, right? So it's not going to automatically work for any mesh. That's going to be important. You should be able to basically place grass onto any mesh, right? That's a good feature to have, and well, necessary if you're doing more than just a little grass rendering test. And then from there though, we generate this like random float, but the random float takes in grass position as this kind of CO thing, right? And so if you look at this math, of course this math is going to be completely deterministic, and we can predict it for a specific like grass position that we pass in, which means that if you're rendering that same blade of grass every single frame, it's going to give you the same result. So this isn't going to be like a random number that changes frame to frame. It's going to be constant per grass blade ultimately. And that's, I mean, I'm assuming that's what we want. Otherwise, all of this would fall apart, right? But what I don't like is that you're using this to like generate a random rotation. It's not actually a random rotation. Basically what's going to happen is, since this random value will give you the same value for each like blade of grass, for each unique blade of grass, it's going to basically take one of your blades of grass and position it facing a particular direction, right? So that rotation though, multiplied with this position, and then also kind of generating this random number, which isn't like the cheapest thing. There's like a sign in here, and also to do rotation Y, like you build up this like 3x3 matrix basically. You've written it out as a 4x4 matrix, but really it's just that inner rotation that you care about. So this, and this can just go away, and this whole kind of row here. So actually one way to like slightly potentially optimize this, I don't know if this will end up being much faster because GPUs love their like 4x4 kind of thing. But if we were to write this 3x3 matrix out, getting rid of all of these things, then you could just do your rotation Y. You know, you take in your rotation, but instead of making this position now a vec4 and then getting X, Y, Z, you can just get rid of like this part entirely, and then this is just going to be and all of this, and then this is just going to be like this mat3 multiplied with this position, right? So there's no reason to make it a mat4 because your translation, the translation section of your matrix is just 0 anyway, and you're not trying to translate, you're trying to rotate. So that's kind of another optimization that I would make. But again, coming back to this, I just don't like the fact that this is all done inside a vertex shader per vertex. Like, we don't need to generate a random rotation per grass blade. We don't need to do that multiplication and actually build up this rotation matrix for every vertex. All of that can be pre-computed and stored inside some kind of storage buffer so that you can just go, right? Because it's all the same. It's all the same for, like, it's different per grass blade, sure, but it's all static, frame to frame. It's not like it's dynamic, right? Like the swaying and all of that, that doesn't, like the displacement that you've got here, that does need to be calculated, obviously, per vertex, potentially, per frame, right? That makes sense. But this stuff, I would just kind of pre-calculate that once when you generate your grass chunk, and then that's it. And that will improve performance considerably. The only reason why you maybe wouldn't do that is if there were some kind of memory considerations, but I wouldn't think that would be much of a problem. If we go back to our grass chunk, it also seems like, I mean, I need to, because you're not using buffer sub data, you're using GL buffer data. So doesn't that allocate memory? Like, wouldn't that allocate this buffer every frame, basically, every time you call render? Because we probably don't want to do that if the blade number doesn't change. We probably just want to allocate this once and then use buffer sub data to potentially stream in grass positions per chunk. But again, like in my world, you'd already have the grass positions pre-calculated. In fact, they are pre-calculated because they're here, right? I think what's going on here is he's rendering each chunk one by one, I guess. And so since each chunk is rendered one by one, we need to set like a new set of grass positions per chunk that we render. It would be kind of interesting to run this through RenderDoc potentially. Is this going to run with my current changes, or have I ruined the shader? Yep, I ruined the shader. Let's get rid of that. Let's get rid of his like 4x4 matrix. We'll just switch to using our 3x3 one. All right, cool, that works. So let's go ahead and run this through RenderDoc and we'll see how it works. All right, so here we are in Nsight because RenderDoc crashed on me twice for some reason trying to capture this. But here we can kind of scrub through this and you can start to see how it's working. So we are actually rendering a lot of chunks here that are barely visible, so that's not a really great lotting system, I think. Well, actually, they did mention a lot system, so we might take a look at what those chunks look like. We just can't see them very well. Maybe there is some hope there, although they do look like just the grass blades, I guess. And then you can see we kind of go through these chunks and render them one by one. So this is how it's happening, and I'm assuming that like for a given draw call, like this one over here, so this is GL draw arrays instanced, and we're drawing, how many are we drawing here? Let's take a look. So 3,906 instances. So that's kind of, I guess, how many instances we have per chunk. This is it being drawn over here. And then if we take a look at all of these details here, then you can see we have like this positions buffer. And if we take a look at the positions buffer, it's just filled with positions. Predictably. Let me just hit configure. I don't know why it's, yeah, I guess it doesn't know what type it is, but what are these vec2s, right? So if we just display them as vec2s, then you can see the data a lot more clearly. So these are like, for that chunk, these are just all of the kind of two-dimensional X and Z positions for each blade of grass. And we have quite a lot of these. We have like, what, 4,000 almost for that given chunk. So that's kind of the reason why we're like setting the buffer data every frame like that. I don't know if I would necessarily do that. I guess it does make sense to dynamically set the data like that. That's okay. The only thing that I definitely wouldn't do though is like reallocate it like that. That definitely does not need to be done if that is what's happening. If we go back to grass chunk, like GL buffer data, like this should be GL buffer sub data with whatever your buffer actually is. And then you should do the initial GL buffer data in your main class. Let me just close this because it's just lagging. So over here in like the grass renderer, when you create this, you should do your GL buffer data, right? And actually allocate the memory here. I think it's safe to assume that every chunk will have the same number of grass blades. Even if it doesn't, you could have a max number of grass blades and then a uniform to make sure that you don't read past that and don't render too many. You don't even need a uniform though, because it's just going to, you know, when you actually do the instance rendering here, you're rendering like your instance count to obviously match how many grass blades you want to render. So you're never gonna pass the buffer, but the point is you could generate a buffer with your max number of grass blades per chunk and then just simply stream that data in if you want every frame like this, and that's fine. Also, you're using GL static draw, which again, if you did create this, not here, but here, like you should have. So if we just do GL buffer data over here, number of grass blades, is there like a maximum we can have, or is it just is it really, it might actually just be the same for each chunk. But let's just arbitrarily set this to something like, I don't know, 4096, right? We'll set the data to null pointer, and we should set this to dynamic draw, not static draw, because you are going to be updating it every frame, and in fact multiple times per frame. So if we just do that, I wonder, and then we come back here, change this to buffer sub data, and then we have an offset of 0, a size of this, and then that's our grass positions, which, what is that? That's a vec2 pointer. Yeah, which is an array basically of vec2s. Like, I wonder if that's going to make any difference to our performance. Okay, it doesn't really look like it. It's still hovering around 160 FPS, and that's probably because I'm assuming the majority of the actual work here is going to be spent rendering like all of those triangles, because there's going to be quite a lot. This chunk bounding box is on frost, and this is like all the math here to basically check to see if it's inside the camera's view, which is good. Now the last thing I want to do is, if we look at the fragment shader, let's have a look at this quickly. So cool, we've got our little fog factor. There's a few different potential equations I guess we can use. Maybe you were playing around with different like fog styles or fog equations or something, but ultimately we set the frag color to, looks like based on the height of the blade of grass, we determine a color between these two, which is okay. Probably wouldn't use a mix for this necessarily. I think I would just define some kind of grass color. So maybe like you could define this as your grass color, and then I would have some kind of like float light scale, and that would be basically the height, because you're kind of mixing between two vec3s here per channel as well, kind of, which is like, I mean, it's going to be the same per channel. It's like going to be just linear interpolation, because height's going to be the same across all, you know, X, Y, Z here. But, you know, you could have your light scale, your grass color, and then your frag color in this case could just be like, you could just do like grass color times equals, you know, light scale. Which for now I've set to height. I'm assuming that's between 0 and 1. And then you can just set your grass color and 1 like that. Let's see what that looks like. Okay, cool. I think it probably should be a little bit darker. Let me actually go back to the 1000 by 1000 resolution, just because I don't like the chunks not being there. And I might actually square height just to make that curve be a little bit like, you know, darker basically, because the values will be lower. Yeah, that looks kind of cool, I think. There is like, it shouldn't be completely black at the bottom, especially with this density. Maybe if it was denser, that would make sense. And the way you could fix that is just by basically adding some kind of minimum to this. So light scale, this is going to be 0, where it's 0, but we could either like clamp that basically so that, let's just say, it doesn't go below 0.2, and that would just kind of clamp it out, or we could add to it so that the curve starts a little bit higher, and you can see this just gets us that kind of darkness, but it's just not to that extent. So there's a few different ways we could do that. That almost seems a little bit too light though. Okay, cool. Now the other thing that I would say this needs is some kind of variance in the color, because at the moment every single grass blade is just like the same green. I mean, like, it varies based on the height of the pixel along the grass blade, but they're all just green, and that's weird. We need like a bit of yellow in there. We need just a variance in color. Now, because you already have that random being calculated in the vertex shader, which is fine, right? I think what I might do, because that's also based on the individual grass blade, not the vertex. So even though we're doing it per vertex, we're actually going to get the same exact value for every vertex along a single grass blade, because it's going to be the same grass position, right? So for each instance, we're going to get the same random value, because this is really the seed, kind of. Not really the seed, but the number we pass in to try and do some math and get a different number out that is seemingly random. So what I'm going to do is just output that random. That's another thing you could use, probably some kind of conventions for your variables here, and you could even like make some kind of like out struct instead of having to use this, because you are using version like 430, so you definitely support that. That would just tidy this up a bit, but it's okay, you know, it's not like it's a big deal. So the output random here is just going to be random. And then if we go back to our fragment shader, we can use this random now to randomize like this color to an extent. So for example, now random I think is going to be between 0 and 1, so we have to keep that in mind. But if we like, for example, want to add a little bit more red to make it kind of more yellow, we could drop that a little bit just so we get some nice greener kind of grass blades, but then add on random. But if we just leave it at that, then it's going to add on either 0 or up to 1, which means obviously this could be as high as 1.2, which is way too high. So we need to multiply this by like, what do I want it to go up to? Like, I guess 0.6. So I'll make it 0.4 so that this can be now between 0.2 and 0.6. Similarly, with the amount of green, I'm going to drop the initial green, because that is going to be the new kind of lowest possible value of green. And then I'll add on this. Now, 0.4 is probably going to be too much, maybe 0.3 because it'll go up to 0.8 in that case instead of 0.9. And then with blue, like we'll drop that, I guess, and then we'll just add on maybe, I don't know, 0.2 up to 0.2. So let's take a look at this and see if we have that kind of variance now. And there we go. So we have a bit of variance now. Now it's not perfect. You can see that it's a little bit, if I kind of zoom in here for a bit, we can see that variance, I think, a lot easier. It's very like, the aliasing is terrible and everything, but especially at that zoom level. But you can definitely see the distinction. Some of them are greener than others. We have a more kind of yellow thing. It looks a little bit cooler, I think, because you have that kind of variance. I would probably also make them just in general be more yellow the higher they get as well. So we're kind of just multiplying it by a light scale, but here you really could mix in your kind of you know, height, where potentially like based on height as well. So if we just do like height times 0.5 plus that, like this is probably 0.5 is probably going to be way too much, but this will probably, yeah, that's just going to give us yellow town. But and we could probably lower the randomness then. Let's lower the randomness a bit. So 0.2, because we've introduced that height now. And yeah, this will kind of make it be a little bit greener below and then go up to a little bit more yellow. And then the floor here, I would make basically the base color. I still think at this like density, they're definitely too black, because you can see that light can clearly come in and hit the area here. If they were like very dense, then I would definitely, you know, make it darker like this. But I just think this is probably way too dark. So I might even make this like 0.3 or something, because they are so sparse. And then you'll kind of see this a little bit better. But the idea is you kind of want the base to match the floor color, obviously, so they fade out kind of more towards that. But yeah, that's kind of, I guess, my grass. And some of the things I would change, of course, this is one of those things you can tweak like forever. The height of the grass also, I noticed, wasn't really, you know, it was very similar. They all seem to just be like this height, you know. Would be nice to see like grass that is, well, first of all, closer together, potentially, like grass kind of clumps, right? But then also maybe some of them are like this big, and then you have the bigger grass blades, but otherwise they're all kind of uniform height, which also doesn't look great. But those are kind of my suggestions and some of the things I would change. But I hope you guys enjoyed this code review. If you did, please hit the like button below. Also let me know, like, if you have any other opinions about all the code we've seen here or about grass rendering. Maybe I'll make a video on grass rendering in Hazel, kind of try and make that an educational thing, because I've got a lot of potential things I could do here. As I mentioned, if you want me to review your code, then send it in to chernoreview@gmail.com. All the details will be in the description below. Don't forget to check out Brilliant at brilliant.org/thecherno. It honestly is such a great place to learn math and various other STEM topics. I will see you guys next time. Goodbye.